figure out why some of this is upside down. What was your name again? Excellent. All right. All right. So we're getting close to that first test. I think it was even scheduled for this weekend. I'll have to look at it. I'll probably push it back a few days. So I'm gonna probably push it back to next weekend.
Okay, next weekend.
Yeah, so if it was scheduled for this weekend, I'm gonna push it back. So exam one, I'm gonna push back. So if it's this weekend, I'm gonna push it back till next weekend. All right, so that show up on here. Sorta, the glitter. Let's see if I can kill this one like that. Okay. We still read it. They can sort of read it. Guys, yell at me in chat if you can't read that. You can still read it?
Yeah.
All right. Yep, good. For some reason, I get notifications that block what we're trying to read. It's good. All right, excellent. So it's in Blackboard. This pen's no better. Play with these till I find a good one. There's our winner right there, first shot. So we're gonna cover some stuff, some specifics that show up that I want to make sure that we've covered and kind of give you an idea so that there's no real surprises. The first one was these solution definitions. My board is getting worked. So the solution definitions. I'm going to just say, go ahead and memorize them. All right. I know when it gets time to the final, I usually like to give those out to you. But looking at the test, it didn't have those on them. So make sure you can do molarity and molality and percent by mass. And this high here, so our solute, which is our mole percentage, okay? So make sure you're able to do all of those, have those definitions kind of ready to roll. The calculations aren't really hard. So if molarity is moles over liters, worst case scenario, I give you something in grams, you got to convert it over to moles. Put it in, all right? Usually we'll tell you the moles, we'll tell you the liters. There's a few that are set up kind of like a lab would be. And so, we might have something that says like a 50 milliliter volumetric flask. And it has 8.2 whatever grams of NaCl. And then they tell us maybe it's 156. That's a little high. Come up with a different number. 57 grams of solution. Then they ask for stuff like molarity and and percent by volume and percent by mass and molality and all this good stuff. So when you're doing this, I want you to always keep in mind the solution is made up of two parts. You've got your solute, which is the one you have less of, and you got your solvent. And when if you're given a whole bunch of these numbers and it's maybe in a big paragraph, it can be confusing. So you come through and you label, hey, this is my solute. And this, if it's in a volumetric flask, this is the solution. And if you see milliliters, you know this is my volume of solution. If you see grams of solution, this is my mass of the solution. Now, why do I have mass of solute in here important? Because I can take that and go to moles of solute. Maybe he has something here that has grams of water. Why is that important? That's my solvent. Maybe I'm going to take that to kilograms to find the molality. And so the hard part for most students is when you're given a whole bunch of information at once, trying to figure out which one of these you're going to plug it in. So start by writing down your definition for it, and then label these. Look at the identity and look at the units. That'll help guide you through it. And so if you're given the mass of the solute and the mass of the solvent, but you need the mass of the solution, you can add those together. That doesn't work for volume, but it does work for mass. But the one that usually gets people is these volumetric flasks. That's going to be of the total solution. That's how those work. Right? So when you use a volumetric flask, I don't remember if you remember using one of those. Let's get a terrible drawing of one. They kind of come to this shape. And the key to this is they'll have one line, exactly one line. And so the way you'll do it, you'll put your solute in. You put in a little bit of solvent until you can get it all mixed up. And then you fill it the rest of the way up with your solvent. And so the total solution will be what's at that line. Usually we measure the mass of the solute when we put it in, and then we'll measure the mass of the flask. We might have to subtract those out, but you guys have had enough lab to figure all that out. Those aren't too bad. But you want to be really familiar with those. I want you to be familiar with the intermolecular forces. Being able to predict, is it a polar molecule or a nonpolar molecule? So a polar molecule has to have two parts. It has to have a polar bond. In other words, they're not touching, but they're close. You don't cross the staircase. The boxes on the periodic table are not touching. Okay? And second part, it has to have what we call a separation of charges. In other words, Dr. Milligan likes to talk about the vectors. So if I did something like carbon tetrachloride, it's terrible, yeah. Pumpkin 2 and me just died a little. Remember, wedges come out, dashes go back. So if we have something like this, it has polar bonds. But they're going out equally in all directions, and they cancel out. So this is it has polar bonds, but it's a non-polar molecule. Whereas something like HCl, it has polar bonds, but it doesn't have anything to make it cancel out. So this would be a polar molecule. Why are those important? Well, when we see our intermolecular forces, we need to be able to predict these things. So when you see something like, let's see, one of the things you guys talked about was fat molecules. And they look like this. Here's a carbon. These are all carbons. All right? And so we get this big, long, fat molecule. It's got this part that's hydrophilic because it's polar. But the whole rest of this is hydrophobic because this part is nonpolar. So what's going to determine all the forces? It's mostly, it'll have a little bit of the dipole-dipole, but it's mostly going to be London dispersion.
So let's see, non-polar, hold on.
So it's got a nonpolar tail and a polar head.
The non-polar is hydrophobic.
Nonpolar is hydrophobic, good. And the polar stuff is going to be hydrophilic. And how do we determine that? Well, water itself is a polar molecule, because we can draw a line and separate the negative from the positive sides.
You've determined that this head is, it's got polar.
Because it has a carbon-oxygen bonds. And carbon and oxygen are not touching on the periodic table. So it's both. But we didn't cross the staircase.
All right, I'm just writing all this.
That's fine. That's fine. Wait a minute.
I apologize, I'm a little slow at writing.
The test uses symbols, abbreviations for our intermolecular forces. The ones at the bottom on this list are stronger. So everything has London dispersion, but it's the only thing that nonpolar things have. If it's a polar molecule, it can have dipole-dipole. We still get on the board? Yeah. We'll put it back. All right. So if it's polar, it has London dispersion, but it also has dipole-dipole, and it's much more important. And HB, that's our hydrogen bonding. You're looking at some electronegative atom with a hydrogen on it, and it needs to have a lone pair. You need to have access to lone pairs to be attracted to that hydrogen. That hydrogen needs to be partially positive. The hydrogen bonding is really important. It adds up real fast compared to dipole-dipole. But if it has hydrogen bonding, it also will have dipole-dipole. Because it's got these plus charges. And then this last one's ionic, and it's crazy strong. It's almost cheap. It's way stronger. So we'll give you a compound. You'll have to predict what kind of forces are there. So we might just give you the formula. We might draw it for you. On these long ones, we tend to draw them. Sometimes we just ask about boiling point or melting point. It's the same trend. And so here's the way I keep up with it. If it's an ionic compound, and here's my boiling point, that's crazy high. Even in melting point for most ionic things, 800 to 1,000, maybe higher. And then you get your way down lower is your polar covalent molecules. And then you get below that your non-polar covalent. And so if I was listing these in terms of my intermolecular forces, here's my I is way up high. Slightly on the top of this list would be my hydrogen bonding. Then I get my dipole, and then down here is just the London dispersion. And so you got to remember that anytime I have these polar covalent, it still has a London dispersion, so we're just adding on to it. Not only is dipole stronger, but it still has London dispersion. Other things that affect where it's going to be on this list, if it's got a higher mass, it's got a higher boiling point. But dipole and hydrogen bonding way outweigh this. So that's just little small changes based off of the mass. This is why when we see one of our more famous examples of this might be carbon with 4 hydrogens. So this we got 16 grams per mole, roughly. And then we got water at 18 grams per mole. Then we'll get, let's do C3H8. 36, 44 grams per mole. Heck, we can look at CO2. 44 grams per mole. Only one of these is a liquid at room temperature. Only one of these is a liquid at room temperature at atmospheric pressure. And that's water. And it's all because of the hydrogen bonding. It also has dipole. These two do not. My CO2, keep in mind, it has polar bonds, but it's a linear molecule. And so these kind of canceled out. So it doesn't really have a polar, it's not a polar molecule. So always keep in mind, H2O is polar, and like dissolves like. Now our book likes to show you data from stuff, and they like to show them in graphs. So they do a thing where they put pressure of the vapor, in other words, vapor pressure. And they'll put that in this axis, and they put down here the temperature in degrees Celsius. All right, and so they might put something like this, and then they'll come over here, they draw a line at 760. Why is 760, and this will be usually torr or millimeters mercury. Why is that important?
Because that equals 1 atmosphere.
That's 1 atmosphere, and that's our normal boiling point, is when that vapor pressure is equal to atmospheric pressure, and atmospheric pressure is roughly around 1 atmosphere. So our standard temperature and pressure then will be 1 atmosphere. And so they'll label these, or they'll ask you in these, and so when we go here, this will be the lowest boiling point, this will be the highest, the next one and higher. And so we expect to see water like out here as one of these. And then they might ask you to come and read this and come down and figure out what its temperature is. They'll give you numbers down here, and they expect you to be able to follow that down. So if it's me and I'm on Blackboard, I'm getting a piece of paper, and I'm coming over and I'm lining it up and following it down. They might ask you, they might give you different points on these. So let's see. Stuff like, okay, so this would be something like, let me do, that's diethyl ether. This would be ethanol. And this would be our water. And the way we can tell these, this is a dipole. It's got a polar bond. It's shaped a lot like water. So it looks like, if I were to draw this, I'm not going to draw my dashes and wedges. But it's got partially negative side and a partially positive side because of that carbon-oxygen bond. This one has hydrogen bonding because of that OH. But water has even more hydrogen bonding because it's got the two H's on that O. And so that's why we see this trend. So they might ask us about different things on this graph, but it's really still based off of this concept. So reading the graph isn't really hard. There's a few of them that are a little specific.
Right. The CH4H2O and their masses.
Uh-huh.
Right, all that stuff.
Okay. Remember, if you don't get it all, you can also get it off the. Let's see. We also talked about our enthalpy of vaporization. When I was teaching this, I always called it HVAC. We'll give you the equations. This is that one that's really weird, crazy LN1. It's big, long. It has to do with where we change temperatures and how much energy it was taken. We give you everything. I just want you able to plug it in. So it's, let me pull up the actual equation here. Ln of the pressure of vaporization, the first temperature over there. Oh man, let's zoom in. Whoa, here's the test. Yeah, that's just what's given to us. So that's one of the things given to us. This Ln P1 and P2, and that's equal to delta H of evaporation over R times 1 over T2 minus 1 over T1. We give you those. And we give you all this stuff. We want to plug it in and be able to find this enthalpy of vaporization. So you're going to have to practice plugging that in. So don't try and memorize this. I'll give you that. All right. Definitely don't want you memorizing that. Let's see. We also spent some time on phase diagrams. Let's see, what did he have? Pressure versus, this is pressure in atmospheres versus temperature. I think he had this in degrees Celsius when you guys learned it. You do it in Kelvin too. It's similar, just different numbers. All right, so I guess terrible looking graph. Let's see how that one is. There's a curve going that way, or a curve going this way, and then straight up and down, and then going that way. Usually we put a line over here. Going across, it'll say 1.00. That's our normal boiling point. And he might have arrows going this way and that way and this way and that way, and just, oh man, all kinds of stuff. So you need to know where a solid is on this graph and where a liquid is. Where a gas is. There's key things we got to be able to label. Where is it a solid? Over here. Where is it a liquid? Liquids are here, or it's like here, and then this could be our gases. Oh, did I tell you wrong? Yeah, this one. This is liquid, this is gas. Liquid, solid, gas. Then up here, this is our supercritical fluid. SCF, if you're gonna abbreviate it. There's a couple of other points on here we need to know. We need to know where, when we're on the line, it'll be a mixture between solid and gas, or between liquid and solid. We need to know where the critical point is. And we need to know where the triple point is, where it's got a mixture of all three. Should be able to find the normal boiling point. And the normal melting point. Oh man. These arrows that go back and forth represent phase changes. They have different names depending on which way you're going. All right, so I'll give you a list of those names and I'll let you look up which one's which. We had vaporization, if I can spell it right. That means somehow. Sublimation. Condensation. Let's see, you're going to have your boiling. So we got melting, deposition. That's the opposite of sublimation. Any other weird ones that you might not know? Vaporization, sublimation, condensation, boiling. Yeah, things that I'm missing any of them. So the way we typically do this, we'll give you one picture and we'll label a bunch of stuff. We'll come in, we'll put a dot, and this is A, and maybe a dot over here, and this is B. Maybe we'll label one of these as E, and then we've got something going on. So if I bring this line down, you'll need to know that, hey, that's the melting point. And here's the boiling points over here. Okay. So maybe we label this one an F or something. So we can ask, the way we do it, we have one picture that we put up, and then we'll ask a whole series of questions based off of that picture. So you really kind of want to be familiar with the picture, because if you have no idea what's going on, you're going to miss several questions. They're mostly based off of these definitions, but we want you to be able to apply them. Okay. I'll get rid of this one here. All right, there's another picture that goes along with those and with this idea of enthalpy of vaporization and enthalpy of fusion. The graph looks like this. We're going to apply heat, and it's usually a constant amount of heat, and then we put temperature over here. Usually that'll be in Celsius. And it's a graph that comes up, comes across. We talked a little bit about this last time. But we want you able to know what's going on in different places. For instance, down here, it's a solid. So what's going on here? Well, I'm going to have solid and liquid, so that's melting. If I'm going that way. If I'm going this way, then we're freezing. So here I've got a liquid. Up here I'm going to have a gas. So if I'm going that way, this at this point would be boiling. And this amount of heat that it takes before the temperature starts rising again, that's related to our mass and to our heat of fusion. So typically we do this on a set amount of mass so we can factor the mass out. And that's a nice way of measuring that fusion. But we are really just interested in you being able to identify where solid, liquid, and gas is and what's going on at the different intersections there. We haven't got to so we're still doing colligative properties. We haven't got to isotonic and hypertonic and hypotonic. So I'm going to give you those prefixes. So that as you do your reading, it's not overly difficult. All right, so iso, that prefix means same. Hyper means more or higher, and hypo is lower or under. And so we talked a little bit about, we were in the middle of talking about osmotic pressure. And this has a huge effect on our body. And so you don't ever give anybody just pure, still working on this?
Oh, I'm so sorry.
Sorry.
I'm sorry.
So
Do we have a freezing point or is it just melting point?
melting point and freezing point are the same. Just depends on which direction you go.
Okay, all right.
So isotonic, hypertonic, hypotonic. We talk about semi-permeable membranes and movement. Well, blood cells, because they're cells, they're semi-permeable. And so when we put a blood cell in to a solution, if it's isotonic, water is going to be flowing out and in. And so we won't see that blood cell change at all. It's just constantly changing out the water and flowing in. Small changes, it goes back and forth, not a big deal. Now, if I throw this into a hypertonic solution, in other words, maybe it's got a lot of salt in it, maybe it's got a lot of minerals, something dissolved. Remember, they're colligative properties. Doesn't really matter what it is. So I'll have my cell, my blood cell, and all the water is going to go from less concentration to higher concentration solute. And so since the solution around the blood cell has a higher concentration, the water leaves. And instead of it coming back, it's all going out. And this blood cell will kind of shrivel up. We call this crenation. It collapses. Okay. Now, if I turn around and I throw this into a hypotonic, now my blood cell is more concentrated on the inside. And so water will come from the outside solution into my cell. My cell expands and expands and expands, and then it pops. You can call it, it explodes. You can, whatever you want, however you want to say it, but it's dead. It ruptures. But it's an overfilled balloon. You put too much in it, and it just can't handle it anymore. Now, we use these for all kinds of things. These are dangerous. This is why when you give somebody, if you go run an IV, they say, oh, you need some more water. They don't just give you pure water. All right? This is going to kill your blood cells. And they got to be real careful when they make up that saline solution. But we also can use this if we're going to store meat, for example. So if I have a lot of meat, I might pack it in salt, and it'll kill the bacteria. Why? Because we've made a hypertonic solution. And it'll crenate all that bacteria and kill off its cells. If we're doing fruit, they don't usually use salt because it'll pull way too much water out of the fruit.
And it'll also make it taste salty.
And it'll make it taste salty and bad. And so they want it to taste good.
Unless you like salty tasting fruits or whatever.
So they use sugar as their solvent. We don't get the 2-for-1 because it doesn't dissociate. But we use sugar, it tastes a little better. And so if you've had fruit that's been stored, usually it tastes real sweet. We've added a bunch of sugar to kind of serve as a preservative. Then we also have artificial preservatives we can add. They're going to do the same kind of idea. They're just looking for ways to preserve it without having to add a bunch of salt. So when I look on my ingredients for, so I've got a cherry Coke here, high fructose corn syrup. Now they just want the taste there, but it also helps to preserve it. Caramel color, phosphoric acid, again, that's mostly for the cherry flavoring, natural flavors, and caffeine. And so when I look, the sugar and that phosphoric acid, they're making this acidic, and they're making it hypertonic solution so that anything trying to grow in that water is going to die off pretty quick. Which probably means it's not real good for me. Okay, so we'll give you pictures like these, and you're going to look at the flow of water. You need to know isotonic, it goes in and out. Hyper, the water leaves the cell. Hypo, the water is going to go into the cell. I also want you to know in this word crenation. All right, when we were talking about some of these colligative properties, I said the book likes to use vapor pressure to explain everything. And I drew a bunch of pictures explaining boiling point elevation and boiling point and melting point depression. The book likes to use this picture right here. And so Dr. Milligan went ahead and put some of these on the test for you. And there's a place in the videos and in the book where he's got 3 of these slides right next to each other. And I guess I could look up the page number. You'll see it as soon as you see it, you'll recognize it. It's got vapor pressure, and it's got chi of the A as I go this way, and as I go that way, this is more outside of the B. So we're mixing A and B, and we're making a solvent. All right, now, so as I go that way, A goes this way, and B goes this way, and then the solution is kind of this intersection right here. This is our solution, this one that goes, connects them. Now, here's the key. If we have very normal, we put them in and everything goes according to our equations, we should all have nice straight lines. And so this is kind of our normal solvent solution interaction. Solvent and solution interactions. In other words, are they doing hydrogen bonding? Are they having dipole-dipole? Are they pushing each other away further? And so our equations, we'll talk about next week, ideal solutions. It's kind of like ideal gases. If they meet all our normal formulas, they're ideal. But we don't always see them as being ideal. So when I do this same kind of graph, vapor pressure versus my mole percentages, or my mole ratios, they're not percentages, sorry. If I see these are fun to try and draw this way. If I see them curved down, like something like that, where they're coming down, this is when we have greater interaction. And then over here, if I see them curve up, so I'm going to just kind of draw to help draw these, I'm going to draw the dotted lines here for reference. But if they curve up, when we look at them, then it's a lesser interaction. These things are repelling each other. They don't like each other. All right? One of the questions on the test basically mixes these up and says, which one's normal, which one's greater, which one's lesser. It's meant to be a pretty straightforward question if you memorize the chapter. So, yeah, if you haven't memorized the chapter, get to work. Or you can just keep up with when it's normal, those lines are straight. Because this is as it's predicted. We expect a nice linear relationship. If I increase the more solubility goes, add more of it, I get more effects from the colligative properties. All right, so freezing point, depression, melting point, elevation. If it's a lesser interaction, it's going to curve up. If it's greater interaction, hydrogen bonding is a big one here, then it's going to curve down. So you can always draw the straight line and kind of get an idea of whether it's curving. It should be pretty straightforward in seeing it once you see all three of them next to each other. But you'll need to know which are the effects. In other words, we predict you add more solute, then you're going to affect the vapor pressure more so. But if they're pushing away from each other, they affect each other more than we predict. And if they're pulling together closer, it actually cuts down on our effect. Because our water and so if we're using water and our other thing we're adding, instead of the other particles getting in the way like salt did, they might be helping the water pack in. Or they might be helping the water boil. Some things will make benzene boils with water real easy. See how am I doing on time? Well, we got a lot going on today. Starts at 10 minutes. I almost had to. Oh man, let's give you some free education. Let's give you a list of the stuff that you guys covered before I got here that I want you knowing that I know is going to be on this test. I want you knowing about all this FCC. I want you to know what it looks like when you got two atoms, how to figure out if it's got two. And BCC, oh man, does it have three? Does it have four? Simple CC, does it have, whoop, that's a terrible W. Does it have one or two or three atoms? Figure out how many atoms are in the,
What is FCC, BCC?
face-centered, body-centered. These are out of chapter 10.
Oh, yeah, that weird, like, cut out.
Yeah,
you
yeah.
know,
And these are the, unit cells.
units.
That's our fancy word for it. All right. Now, I'm gonna tell you right now, knowing those definitions, being able to recognize which one's which, those are all important. Being able to figure out what percentage of the atom is in the corner for each one, so that you can figure out how many atoms are actually in the cell. So the number of atoms in the cell. They give you a picture. That's one of the harder questions we see on there. Now, the hardest one I saw on there was they're going to give you some X-ray data. And they want you able to calculate molar mass. And they'll tell you, let's see, I can tell you, it was a face-centered cubic. So you're going to have to use your equations on that for finding R, the radius of the atom. And find so you'll have to get remember it's grams per mole, or molar mass, and that's your calculation. If you haven't practiced that, let's see, chapter 10 was a long time ago, 2 weeks ago. Go back and practice that. It should show up on some of those practice quizzes. Go back next week to ask questions on it. Did somebody have a question?
Yes, I had a little hard time finding the radius of the atom in body-centered cubic, because face-centered cubic is basically easy because you have 4 R's in the diagonal, right? So what is the basic body-centered cubic story?
So you're gonna have this one here, and you have this one here. I don't know, you're asking me these hard questions. We're out of time. Oh, no, we'll have to get, no.
Oh, I can.
Shoot me an email and I'll look that one up. I don't have it immediately in front of me. Hang on, I do somewhere.
That's okay.
Somewhere I have it right here in front of me. Interest, I gotta get back to it. It has been a long time since I did X-ray stuff, but you know, I did base a lot of my research on similar effects, so you would think I would know all this stuff. Yeah. Body sim. It is back here. Usually, well, I was gonna say usually they. Oh, okay. Yeah, usually they touch. The ones that they usually ask you about. So if I'm looking across the diagonal here, I'll see a curve here, I see a circle, and then I'll see a terrible picture of a curve here. Can you guys see that?
Yeah, that's for face-centered cubic, right?
Okay, and then the body's gonna be back a little bit. You kind of have to go from like this back corner up to this corner.
So we're,
You
I'll
see what I'm
look.
saying? It's,
Yeah, I
it's
mean,
the same, it's the same kind of idea, but instead of going across two front corners of a block, if I'm looking at this, then I'm gonna have one here and I'm gonna be going kind of this way instead of going across the front. It's really hard to draw in 2D and project over here.
yeah,
But I'll get you that equation. Let me write that down and I will get back to you on Monday with that. How about that? And I'll get a pretty picture.
that would be perfect. Thank you.
All right.
I-
'Cause it's pretty much some kind of R squared over L and, it's just, you have to use Pythagorean theorem. That's what it is.
Oh, well, that worked perfectly for face-centered cubic. For body-centered cubic, it didn't work really well for me.
Okay. I'll play with it and I'll get it to you,
On
Uh,
Monday.
on Monday. And so that's good. So there may be, if there's a quiz you haven't done, so, yeah, I didn't make this announcement yet, but if there's a quiz you haven't done and it said, some of them will say they're due on Friday or due today. If you're not ready for it, don't freak out over it. I'll still grade it when it's a little bit late.
Okay.
And I'm
Well,
not gonna take off. Okay, go ahead, Julia.
Yeah, the quiz that I had said there was an X data given, and it said figure out if it's a face-centered or body-centered. Well,
Oh,
I
okay.
solved it for face-centered and it matched, so I got lucky. I just didn't know how to solve it for body-centered. So I'm
Okay.
good on quizzes. I just don't understand the body-centered cubic a lot.
Let's see, so body centered, it's gonna be the volume is linked to the cube. Let me. Yeah, I don't have that immediately in front of me. I'll get that to you.
Yeah, I'm sorry. Thank you.
No, that's fine. That's a good question. You need to know that one. So, I will, get that one to you, but I'm pretty sure that it's very similar and you just go across that other corner. But you said that calculation didn't work out, or you knew how to do face centered, but you didn't, the body centered wasn't working, right?
Yeah, Pythagorean theorem works perfectly for face-centered. Body-centered, I didn't know how to count the radiuses, how to go from diagonal, since there wasn't that intermediate medium piece on each side.
Right, right. So usually you figure it up, that it's two atoms and you find the total volume. But yeah, I'll have to figure out, how to find the radius. So that's the one part of the calculation I guess you could use the volume and solve backwards and get the radius, but I'll get it for you.
All right. Sorry. Thank you.
Oh, that's a good question. Don't ever apologize for asking good questions. Anybody else? All right, we're gonna end it here. Big announcement, next week on Monday, we're gonna be switching to Zoom. Because you guys haven't had a difficult enough time. We need to switch to change all the technology up on you. So I'm gonna switch us to Zoom on Monday. I'll send out the Zoom info probably this afternoon as soon as I'm done with this. I've got a meeting, a series of meetings. So once I skip those out, send those out, it's pretty much a click and sign in, all right? Zoom tends to work better because you'll have a big picture instead of me being in one of these little corners. It's easier for me to download and save, and then I can upload it into Blackboard a lot faster. We don't have to wait on Microsoft. And then I don't have to forget to hit record sometimes. That's always a big issue. So, and then, so my other classes say they like Zoom. We'll try it out. So we'll see you guys. Have a good weekend and be safe. All the people that didn't wear masks last weekend are out there running around. Many of them aren't showing symptoms yet. Wear a mask this weekend. This is one of the more important weekends. All right. So take care. Be good, everybody.